Hello and welcome. I'm Claudia Rizzini, the Executive Director of the Radcliffe Fellowship Program at Harvard University. It is my pleasure to introduce our speaker today, Judith Lok. If you've ever taken a statistics course, you have probably heard the phrase, correlation does not imply causation. Traditional statistical approaches often capture a fraction of the real-world behavior. In contrast, Judith's research concentrates on statistical methods that elucidate causal relationships between variables and outcomes. Crucially, she applies these methods to non-randomized data, particularly in healthcare and biomedical research, where establishing causation and not just correlation is essential. From maternal and child health and overdose death to HIV/AIDS, antibiotics-resistant bacterial infections, and COVID-19, Judith provides critical analysis together with clinicians and public health researchers. By examining treatment options for patients and evaluating alternatives, she provides crucial insights that help physicians shape treatment plans. As an educator, Judith has developed a novel course that teaches the mathematical statistical theory behind causal inference, a concept that has become a cornerstone of statistics. While at Radcliffe, Judith is writing a textbook on drawing conclusions from non-randomized data. It will be the first comprehensive textbook addressing the statistics behind many causal inference methods, filling a crucial gap in available training materials. The ability to infer causality from non-randomized data has wide-ranging applications in many disciplines, from biostatistics to epidemiology, from economics to political science. The Q&A session of the event today will be moderated by Jane Chang, our Edward, Francis, and Shirley B. Daniel Fellow. And now please join me in welcoming Judith Lok to the podium.
Thank you, Claudia, for this wonderful and flattering introduction. First of all, thank you to all the Radcliffe staff and my fellow Radcliffe Fellows for making this environment so welcoming, so enjoyable, and also so productive. I'm truly happy that I can spend my sabbatical here. I am going to talk about some of the aspects that I will cover in my book, Causal Inference, A Statistics Playground. And what I will convey to you here is that we can draw causal conclusions and we can come up with precise conditions under which these conclusions are valid, which makes causal inference, and no, thank you, Claudia, for making that mistake, causal inference. Okay, so causal inference is there to try to draw causal conclusions from data. Some people consider randomized clinical trials part of causal inference. It's sometimes also called the gold standard of causal inference. But there's also a lot of observational data around where investigators are not interfering in who gets treated and who does not. And we still want to also use that data these days to draw causal conclusions. So when you see this picture, I think many of us think, great, spring may be coming. Not yet, but soon. So other people look at this picture and may think, oh no, allergy season is coming soon. So it is known that allergy medications affect allergy symptoms. They help reduce them. Randomized clinical trials have told so, and it is conclusive evidence that they work. But these days, people are often also interested in how do these treatments, these allergy medications, work in the real world. So maybe you want to see how it works in the real world. Maybe there are people who don't regularly show up in randomized clinical trials, and maybe the people who are taking the allergy medications now are different from the people who were taking them when these trials were taking place. So let's picture this idea. Let's try to figure out from data that we collect now on the street without randomizing the medication to figure out whether allergy medication work also the way they are being used in practice. So let's suppose we go on the street and we ask people a few questions. Let's picture ourselves in Harvard Square. There's plenty of people there. We ask them, okay, have you been taking allergy medications in the past 2 weeks? And because we're interested in the effect of allergy medication, we will also ask them a second question. Did you have any allergy symptoms over the past week? Okay, so we will get all kinds of answers. And we have this group on the left that says, no, we are not taking allergy medications. And we have this other group that says, yeah, we have been taking allergy medications over the last 2 weeks. 2 different groups. Now, the people who were taking these allergy medications probably took them for a reason. At least at some point in their life, they have suffered enough allergy symptoms that they decided to take the allergy medications over the past 2 weeks. In the other group, there will be plenty of people who are not taking allergy medications simply because they never experienced any allergy symptoms. Maybe they had a few, but they may not ever have had any allergy symptoms. Now, these treatments from randomized clinical trials, we know that they reduce symptoms, but they don't eliminate the symptoms. So in the people who have been taking the allergy medications, some of them, or probably even most of them, still will experience some symptoms of allergies. In this other group, there will be a majority, maybe even, of people who are not experiencing any symptoms simply because they don't suffer from allergies. If we now want to look how the medication works in the real world, if we don't collect more data, we are lost. Because the people in this treated group, the people who are taking the allergy medications, all of them have at some point had allergy symptoms, whereas the other group, many of them never had anything. So the comparison is not a fair comparison. It's biased in the disadvantage of the treated people. Because the treated people often have a lot of allergy symptoms. The untreated people, many of them don't. So it's not a fair comparison. And that is at the core of why causal inference comes about. What can we do? What extra information do we need to collect in order to draw causal conclusions, even when these treatment decisions have not been randomized? When treatment decisions have been randomized, a flip of the coin decides who gets treated and who gets not. So if we see difference in outcomes between the treated and the untreated, we are typically fairly confident that we can attribute that to the treatment effect. Now, if we have the treated and the untreated, and the treatment has not been randomized, then treatment differences between the treated and the untreated can arise from 2 different reasons. It can be that the treatment has an effect, but it can also be that the difference between the 2 groups can be attributed to the fact that pre-treatment, the treated and the untreated were simply different populations. This is a particular example where I had been asked to estimate the effect of Casavi compared to colistin for the treatment of, and let me say it correctly, carbapenem-resistant enterobacteria. I don't remember. So these are highly resistant bacterial infections that hospitals hope to avoid in any given year. They are dangerous, they can lead to death. And you can see that in this picture, especially in the picture on the left. You can see that there's quite a bit of patients who die. And the death is the black part of the graph. What you see here is hospital death over time. So when you look at the right part of that figure there, that is hospital death, and it is the total probability of hospital death over the first 30 years in patients who have been treated with colistin. So on the left, you see what what happens under colistin. On the right, you see what happens under Casavi. Sorry. On the right, you see what happens under Casavi. On the left, you see what happens under colistin. So this is not a full story, because I haven't actually told you exactly what I want to know. So I'm going to walk you through what happens in this picture, how to interpret it, and even a little bit about how we created this figure. So the first thing that we noticed, the people who are being treated with Casavi are not the same as the people who are being treated with colistin. There are indications of severity that affect these treatment decisions. So what we have to assume is that we know why these people have been treated the way they have been treated. And that is the trick to disentangle the effect of the treatment from the reason why it was being given. In other words, the difference in pre-treatment populations. So we have to get a hold of what factors into these treatment decisions. In the case of medical applications, that is usually fairly easy, at least in a qualitative sense, because most of the time a statistician doesn't work on these projects on their own. They have a bunch of clinicians that approach the statistician with a causal question, and those clinicians have a clear idea about what factors into these treatment decisions. The importance is then that the things that affect these treatment decisions have to be collected and available for analysis. So we have to have available for the analysis all the factors that affect both the treatment decisions and, in this case, the disposition over time in patients had they been treated with colistin, and also the disposition over time had they been treated with Casavi. We need to have the common causes of the treatment and the outcome available for our analysis. So before we can do any causal analysis, we have to think of a clearly defined causal question. This is part of being a causal inference statistician. We have to first, with the people who know about the subject matter, phrase the question really clearly, because it's not like in a randomized clinical trial where we have this population and it's clearly defined. We have inclusion criteria, exclusion criteria, and all clearly defined. In an observational study, often the question is not really clearly defined a priori, so we have to set it up in collaboration with the clinicians. So in this case, we talked about what is the population of interest that we want to compare under Casavi versus colistin. So in collaboration with the clinicians, we decided to have the population be everyone in these clinics that are participating who is treated for these highly resistant bacterial infections with either Casavi or colistin. So that will be our population of interest. This is the first step in what Jamie Robbins and Miguel Hernan have been proposing here at the Harvard School of Public Health as emulating a clinical trial. When we emulate a clinical trial, we first have to say, this is our population. Then the second thing that we need to do is figure out, okay, what is the question that we want to answer for this population? So the question that we wanted to answer here, what would be the disposition over time, people dying in the hospital, people being discharged home, what would be the disposition over time of our study population had everyone been treated with Casavi? And then also we want to do the same for colistin. So what if everyone in this population being treated with colistin would be their disposition over time? So now we have a causal question. Next question. We have an observational study, so we have to figure out what all the confounders are. Hopefully, before even touching the data, we have to have these discussions with the clinicians. After some time we came up, I think, with at least 10 or 12 confounders. We didn't have a lot of data points because it's rare, these highly resistant bacterial infections. So we had them list them in order of importance. And in the primary analysis, we included only 2 confounders: the type of infection, bloodstream or urinary tract or other, and a measure of disease severity, the PIT score. We dichotomized it with a threshold of 4. In a sensitivity analysis, where we didn't create confidence intervals anymore, we also looked at including more confounders. We had 6 of them. The results didn't change so much. The point estimates didn't change so much, which gave us some confidence that maybe we had it kind of okay. That being said, from a randomized clinical trial, we can always draw stronger conclusions than from an observational study because we are making more assumptions. In this case, we are assuming for the primary analysis that the only confounders are the type of infection and the PIT score. Okay, then what type of analysis did we do? And here it gets more technical, but for me then more fun. So you have to bear with me. So what the clinicians came to us, they wanted to do inverse probability of treatment weighting. They had heard about other people doing it and they thought it was cool. So that's what they wanted to do. So we are going to do inverse probability of treatment weighting. It's a perfectly valid method, so why not? So what does that do? When we look at, suppose you have this one person treated with Casavi, but of this type of patient, maybe with the same severity score and with the same type of infection, we have maybe 5 of them in the other group, in the colistin group. And in this group, we have only 1. But there's 5 in the colistin group. Then we have to give more weight to this one person in the Casavi group that then has to represent more people, because otherwise it's not a fair comparison. So by weighting the population, we give a weight to each of these patients, not just to this one patient that was treated with colistin. We give everybody a weight and then do the weighted analysis. And then come the statisticians and then can even create point estimates and confidence intervals with reliable coverage under the assumptions that we have all the confounders measured. There are a few more, but those are less important. So that was our primary analysis, inverse probability of treatment weighting, indicated by the clinicians and a perfectly valid method. But in causal inference, we make a lot of assumptions. So it's always wise, if you can, to do the analysis in more than one way. So the statisticians on the project, instigated by me, because I knew most about causal inference in this group, was, okay, why don't we also do something else and we do what we call a conditioning argument. What does that mean? For example, we look in patients who have a urinary tract infection and a PIT score of 4. And we look at what is the treatment effect in such a patient. This is a fair comparison because we have conditions on all the confounders. So this is a perfectly valid comparison, PIT score of 4 with urinary tract infection. We compared the people with Casavi with the people with colistin. And what we can do now, we can combine all these conditional analysis and weighting for how the study population is. So if we have, say, 5 people with this type of confounding values, we count them as 5. We count this difference with 5. And if there's 10 people with some other covariate combination, we count them as 10. And then we just average. So this is just a totally different approach than the weighting approach. So it's important to then compare the results. And we got lucky because we had been so careful discussing all the confounders that this secondary analysis got us almost the same results. And then we got this picture here. So now we can really talk about this picture. You see here on the left is what happens under Casavi. You see that the probability of hospital death increases over time because we look at hospital death by 10 days and by 30 days. And the bottom, in the light gray, we see the probability of being discharged home. Over time, more and more people are discharged home. It's the probability of being discharged home by day 10 and by day 30. On the right, we see what we think would have happened to this entire population had they all been treated with colistin. And you see that we expect that more people would have died in the hospital and that fewer people would have been discharged home had they all taken colistin. This is a trick that we statisticians often do. We make pictures. But when we look at these pictures, you see that every little bar that is there is just a percentage, a probability. So this is just a lot of probabilities calculated all the same way. So we automate that and we get all these pictures. So it's just a lot of probabilities that are now presented in a graphical way. And of course, in the manuscript, we have also created the probability of hospital death by day 30 and created confidence intervals for the difference and all that kind of stuff. Okay. Now something completely different. I wanted also to say a few words about mediation analysis, indirect and direct effects. So what are indirect and direct effects? Indirect and direct effects are a way to decompose a treatment effect into a part that is mediated by a mediator, say a patient characteristics, maybe it's someone's blood pressure, and another part that works through other pathways. For example, it could be that we are looking at the effect of blood pressure lowering medications on heart attacks, and we are interested in how much of the effect of the blood pressure lowering medication works through the effects that the blood pressure lowering medication has on blood pressure, and how much works through other pathways, whatever they may be. Another example, and one that I want to talk about today because I was involved in the analysis, is in COVID-19 patients admitted to the ICU. What would be the indirect effect of a treatment that eliminates positive neutrophil nets? Beautiful pictures. A treatment that eliminates positive neutrophil nets on the final SOFA score at ICU discharge. So the final SOFA score at ICU discharge is a measure that ICU clinicians like to use to indicate how well somebody is doing at ICU discharge. So they wanted to know actually something different. The clinicians wanted to know something different. But I will get to that. So mediation analysis was popularized by Baron and Kenny in 1986 in their seminal paper that nowadays has 125,000 Google Scholar citations. I'm not kidding you. And it changes every time they give a presentation. I have to look how many do they have now. So many of these citations are actually from the last 10 years. So this is an approach that has been used a lot in the medical sciences and in psychology, and is increasingly also used in the social sciences. So maybe I can do, yeah. The interpretation of an indirect effect that Baron and Kenny give, first, treatment causes the mediator, then that effect is continued through to the outcome according to the outcome model. In other words, first the treatment affects the mediator, and then there is an outcome model that says how the outcome would have behaved after that. The direct effect is the effect through other pathways. Causal, indirect, and direct effects have been starting in 1992, I think, and there's actually a lot of discussion on how we should define them, how we should interpret them, but I'm not going into that now. So ICU doctors often look at the SOFA score at time 1 as an exposure. I had a little bit of a hard time when I first talked with them, but it is a score. It's how people are doing. Isn't that the covariate, the patient characteristics? Why do we see that as an exposure? But they insisted, yes, it's like an exposure for us because it tells us how much badness these people have been exposed to. So they wanted to do mediation analysis because they were interested in desperate positive neutrophil nets. They had fancy methods to measure it. They're still finding out how best to measure it, how often, and then how to average and all that kind of stuff. So it's a new measure that they're looking at. It's desperate positive neutrophil nets, beautiful colored pictures. I don't know how to count them, but somebody does. So this is the SOFA score that they wanted to use as their exposure. It's the SOFA score at ICU admission. It's a measure for how well the patients are doing when they come into the ICU. Their mediator that they wanted to study was desperate positive neutrophil nets. And then they wanted to know what is the effect of SOFA 1 score, how bad people are at ICU admission, on the SOFA 2 score at a time of ICU discharge that is mediated by these most desperate positive neutrophil nets. So yes, we can do this analysis. We can figure out how this mediation analysis works, and I did that with them. But before doing that, we talked a little bit more like, why are you really so interested in this question? And it turned out they actually had a patented drug. And this patented drug eliminates, at least in rats, eliminates desperate positive neutrophil nets. But before they can bring this drug to test, they have to show that it mediates. So that was what they were doing. They wanted to show that it mediates so that they can maybe get permission from the FDA or from regulatory agency to try this drug out in humans. So I drew this picture for them that to me looked more like a general mediation analysis question, because now we have a treatment, not the SOFA score at ICU admission. We have this treatment that I have patented. It works in rats, okay, fine. But what they're hoping is that this drug will also eliminate desperate positive neutrophil nets in humans. So they are going to try to show that it also works in humans and that the desperate positive neutrophil nets will be eliminated. So these are still, the mediators, still the desperate positive neutrophil nets. And then the outcome remains the same, the SOFA score at ICU discharge, a measure of multi-organ failure. When we do mediation analysis and we take a causal approach to it, we also need, on a graph like this, all the common causes of everything else in the graph. And from this picture that I showed you just now, you see that the SOFA score affects the mediator, that's for the positive neutrophil nets, and the SOFA score at ICU admission also affects the SOFA score at ICU discharge. It's a common cause. So it needs to come in this graph as well. Why does it need to be in this graph? Because we want to follow the approach by Baron and Kenny and say first treatment affects the mediator. Well, we have an idea about what they hope at least what it will do. Eliminates the desperate positive neutrophil nets. M equals 0. So this arrow we have under control. But then we look at this arrow. We want to know how this absence of desperate positive neutrophil nets will then affect the SOFA score at ICU discharge. For that, we need this SOFA score at baseline as well, because otherwise we don't know, when these neutrophil nets have been eliminated, how these people will fare. That will depend on how they were at the start. At least in theory, it may depend on that. In COVID patients admitted to the ICU, desperate positive neutrophil nets predict the outcome SOFA scores, and a higher SOFA score indicates a worse outcome. And so they have this patented drug that hopefully will eliminate desperate positive neutrophil nets, and we were able to estimate the indirect effect of that drug. not the overall effect, because there are no outcome data under treatment. This drug has never been used in humans. So we used the estimate of this, or the hypothesized effect of this, with how this SOFA score then would have evolved in the absence of desperate-positive neutrophil nets. And we got an estimated, so one more thing, the ICU clinicians are most interested in improving the SOFA score of people who come into the ICU with a bad SOFA score, and that means a high SOFA score. So they were most interested in doing this analysis in patients who were really not doing well at baseline. So we found a decrease in the SOFA score at ICU discharge of 1. And we created a confidence interval for that. And the ICU clinicians have assured me that that is a meaningful, clinically meaningful effect. In other words, they hope that this drug that eliminates desperate-positive neutrophil nets, that will actually help people. So we are now trying to get funding to study it a little bit more. Why was I thinking about drawing this graph? I was thinking about drawing this graph because previously I had worked with this graph, where it is even more important to estimate the effect, the indirect effect of a treatment without outcome data. And why is that? Because this is an HIV example. And in this HIV example, we are looking at HIV cure. The current HIV cures are not very safe, are not very effective. We hope to get there, but at this point they're maybe prolonging what we call viral rebound by 4, maybe 8 weeks. Nothing for a lifelong chronic disease. So in order to test HIV, in order to test HIV cures, it's very important to be able to figure out what are the most promising ones. And it turns out you can use outcome data under no curative drug to get a sense of what is the most promising indirect effect of drugs that reduce several aspects of what is called the viral reservoir. The viral reservoir is the big problem of why HIV is still such a chronic and nasty disease. Something completely different, but also a little bit related. In causal inference, we often want to figure out what we even want to know. In the example of Casavi versus colistin, I told you we have to find the study population and a clear-cut question. In the case of causal mediation analysis, there is a lot of debate about how exactly should we define a mediated effect. In this case, we were looking at summarizing a clinical outcome measure when some patients die. That happens a lot when we look at the effect of statins on neurocognitive outcomes, a project that I'm currently working on. We're looking in the elderly, so some patients will die. And there are several approaches to deal with it. The most common is probably saying, okay, we just compare the people on statins who are alive with the people off statins who are alive. Well, this is unfair comparison because statins save lives. And so we are comparing apples and pears. Like in the case of the allergy medications, we are comparing people who are relatively healthy with people who are less healthy. So we don't want to do that. We don't want to compare those who are alive under one treatment with those who are alive on the other treatment. So what then? So here's an example of people. There's people with a good neurocognitive score, people with a bad neurocognitive score, and we want to know what is the prognosis of the average person. So this is on scale, let's say, so it's 100% total, and you see that there are more people with a bad neurocognitive score. So in this absence of death, we probably say the average person has a bad neurocognitive score. the median person. In this figure, there are a substantial number of people who died. More than half of them in this picture. Fortunately, never worked on a study like this. So what would we say that happens to the average person in this case? One would probably say the average person dies. The median person dies. And that's all there is to what we call the survival incorporated median that I first applied in an applied paper in a journal that is called AIDS, where we summarized how the CD4 count changes over time. And we looked at the median CD4 count, and we said, what do we do with the people who die? Well, we just create such a figure, but incorporate everyone. Dead people, people with a bad neurocognitive score, and people with a good neurocognitive score. Making this figure, you see that I value being alive with a bad neurocognitive score as being better than being dead. Some people may discuss that or dispute that. Then they can take a different figure. Fine. What we want to do then is say, okay, we look right in the middle of this distribution and take the median. So in this case, one would say that the average person has a bad neurocognitive score. So we don't restrict to this. We look at the whole picture and we organize everyone. It's called a composite outcome strategy. And we look at this and we say the average person, the median person in this case, has a bad neurocognitive score. So why is this important? Because it's a very simple measure. If we have a randomized clinical trial, treated, untreated, we organize these people and we just look right in the middle of the distribution and that's it. There are other scores that people have been looking at, and that is a much researched score is what is called the survivor average causal effect. And what is the survivor average causal effect? It's the average effect of the treatment in those people who would have survived both under treatment and under control. So who would have survived under both treatment options? It's a clear-cut population, and for biology, it's very important because if this has a positive effect of the treatment, we know that there's a group who benefits from the treatment. However, it turns out to be a very scary measure if you use it in to inform clinical decision-making. We have been able to construct an example where whatever cutoff you choose between a good and a bad neurocognitive score, the probability of being alive with a good neurocognitive score is better under treatment A. Whereas the survivor average causal effect says that the advantage is for treatment B. It sounds maybe counterintuitive, but what happens here is this happens especially when one of the treatments has a higher probability of death. And those, if you estimate with a survivor average causal effect that there is a trade-off between good neurocognitive scores and survival, then you get this kind of confounding where it's really dangerous to base your clinical decision-making. Because maybe some of those people who have been saved by the treatment, some of them may also have had a pretty good neurocognitive score, and some of them not, but you have a lot more neurocognitive scores, so you get a bias. I have 4 more minutes, so this goes out of the road. I would like to thank my collaborators, Vicky Herrera, and especially and the group of doctors that I worked with on the COVID treatment data. I would also like to thank Ron Bosch, who worked with me on mediation analysis and various other projects. He has been a long-time collaborator of mine. And then I've been working with several PhD students. The survival incorporated median, I'm working with Qinyan Sheng. He is done now as a PhD student. Ari is also done mediation analysis. Kelly Kang is done regression not to the mean, and various others. Most of them have been at Boston University. Brian Sharkey was for my time at the Harvard School of Public Health. And then I like to say that I am standing on the shoulders of giants. So many people have been instrumental in getting me where I am now. Of particular importance, Richard Gill, Aad van der Vaart, Jamie Robbins, and also at Boston University, Tasso Kaper and Eric Kolaczyk, who allowed me to be a mathematical statistician again after my errands in biostatistics. And thanks to my research partners, one of them is here, Emma Miao, Lia Wang, and Ahmed Hussain. Thank you so much.
Thank you, Judith, for a very nice presentation. The talk is now open for questions, so please submit your questions online. I will start with a question from the audience. How did you get interested in the discipline of statistics?
I was a pure mathematician major first, because I was at a university where they really valued pure math, and I could do pure math, so that was my thing to do, and I kind of went with the flow, until at some point in time I was like, wait a moment, I'm starting to ask the wrong questions. Like I was asking in a course on infinite dimensional Lie algebras, I was asking what this was used for, and the answer was, well, we think that there are some physicists that use this kind of thing. And I started to feel a little uncomfortable because I wanted to have something tangible now. I was not as patient as my pure mathematics colleagues. I admired what they did, but I wanted to see more tangible results. And statistics is really the discipline. They say you can look in everyone's backyard. It's really fun. You get to work with a lot of interesting, real examples that can make a difference in people's lives right now. And we don't have to wait and see what happens. So I was impatient. I guess that's why.
We're glad that you were impatient. So we have two questions related to the highly resistant bacteria. The first one is, it is often heard in the news outlet that the widespread prescription or usage of antibiotics is the cause of the superbugs.
Yeah.
Is that really a cause or a correlation?
I have not investigated this causal question. I have read the news like most of you, I think. So as far as I know, it is part of the cause of why we are where we are. And as far as I know, so in the United States, people are using more antibiotics than in some other countries.
Okay, the follow-on is for the comparison that you made with the colistin and Causal. How different would your results look if you just did the most naive analysis possible, looking at percentages of outcomes for respective population with no fancy weighting parameters?
So this is actually something that happens quite a few times, that you see that your results are actually not that different from if you do a crude analysis, but there are examples where they are very different. So what happens if you do this crude analysis is that most likely people will just not trust your results because they will say, but these people are different from these people, so why do you even call this causal? So I think part of why we do this method is to reassure ourselves that the differences that we see in daily life are actually truly there. So it is kind of a safeguard against making conclusions that are not really there. Sometimes you see that it doesn't make much of a difference. There are cases, however, where it does make a lot of a difference. There is important work by the group with Jamie Robbins and Miguel Hernan, who have shown that naive analyses can really lead to erroneous answers.
Thank you. And we have another question here. related to examples that you might be able to tell us that what could have gone wrong in epidemiological studies if inappropriate methods are used. For example, where patients were given wrong drugs based on the wrong study findings.
So I may be wrong with this, but I think there was this hormone replacement therapy in women, where observational studies analyzed the wrong way. Was estrogen? Thank you. So the observational studies were analyzed the wrong way, and people were actually taking these medications. And then in randomized clinical trials, it was shown that it was not beneficial or even maybe harmful. So it can happen.
So you mentioned randomized clinical trials a few times. So the next question is, a randomized clinical trial often takes a long time and can be very costly. Is the causal inference type of study that you do could replace or supplement those studies?
I think more supplement than replace. I think that a new medication is never going to be used widely just from observational data. But observational data can often be used to select the best possible treatments in the best possible population for a clinical trial. So it can be used to figure out which people to include in a randomized clinical trial, and it can also be used to select the treatments that are most promising for clinical trials. There are settings where clinical trials are really problematic and where maybe observational studies are all there is. And I think this could especially be in populations of rare diseases.
Thank you. In the social sciences, one common method for causal inference is based on instrumental variables. Could you say a bit about why this does not seem to be commonly used in the epidemiological research?
Instrumental variables are actually increasingly used also in medical research. It's a method that comes from economics, and people have studied it, and it's a valid method. It is often hard to find an instrument. That is one of the things, because an instrument has to be something, for those of you who don't know what it is, an instrument is something that affects the outcome only through the treatment. And it is also used when treatment is not randomized. And because you can estimate the effect of the instrument on the treatment and also the effect of the instrument on the outcome, you can combine those results to get an estimate of the effect of the treatment on the outcome in the treated. So it is not an overall effect of the treatment in the overall population, it's the effect of the treatment in the treated. It is increasingly used in medical applications also, but not as much. I think because in medical studies, people often try to get a hold of the confounders of interest, and then there are other methods which are probably more efficient to get the treatment effect.
Thank you. What are your thoughts on integrating machine learning methods or other data discovery methods into causal inference approach? On the whole, are any of these methods helpful, or are they leading us further away from the high-quality causal inference?
I think it's an especially interesting line of research. If I hadn't been here writing my book, Statistics, a Causal Inference Playground, Causal Inference a Statistics Playground, I would probably have been researching more about machine learning methods. I think they're very promising. I think they can be combined with causal inference. When you think about this example that I had there about colistin versus Casavi, what we were modeling was the probability of Casavi, because that is how we estimate these weights. How should we weight the population so that the two populations are comparable? To do that, we estimate the probability of getting Casavi and the probability of getting colistin. We could use machine learning methods for that as well as any other method. I haven't done it, others have. When we look at this conditioning argument that I told you about, we look at the conditional treatment effect first. What would be the conditional treatment effect, conditional on bloodstream versus urinary tract versus other, and conditional on the PIT score? That conditional treatment effect we could also try to estimate using machine learning methods. I haven't done it, others have. One issue with the machine learning methods that I currently struggle with a little bit is that it's very hard to create confidence intervals for these estimates. And in medicine, probably more than in any other field, we can never report a result that is just a point estimate. We have to say something about how reliable this result is, and for that we create confidence intervals. For those of you who don't know what a confidence intervals is, it's like a net with which we try to catch the truth. And if that net is wide, we are catching the truth with very high probability. And if the net is a little bit smaller, we catch the truth, obviously, fewer times. So what we try to create in most medical applications, we try to get a net that catches the true parameter 95% of the time we use it. And that is, if we would repeat the study 100 times, or if we do like 100 different analysis, the 95% confidence interval, we try to catch the truth with our net of confidence interval like 95% of the time. And that is an issue with machine learning that I would be really intrigued to see solved and maybe work on in the future.
Thank you. And we have two questions related to the team that you're working with. Can you talk about how you manage working on teams with non-statisticians? Are physicians and other non-statisticians you collaborate with receptive to your methods and to ask their questions in a causal way?
So they sometimes ask their questions in a causal way, but most of the time it's rather vague. The effect of this on this, no population defined. But usually they come to me because they want something. So last time it happened was they wanted me because somebody had told them that they had to. That was not a very good start, but then they started to explain their ideas to me. And I got really intrigued and asked questions and showed interest, and they were like, maybe this person is fine. And we talked more, and we phrased causal questions, and now I'm working with them on a regular basis. So it's also a matter of just showing interest and try to grasp also the medical side of the problem and to really delve into it. And for causal inference is more important, I think, than for many fields of statistics, because if you have randomized data, you don't need to bother too much about what the question is. You compare A with B and that's it. But in causal inference, it's important to figure out what is really there. Why are we missing these data? Why are people doing what they are doing? So you have to delve into the subject matter. And I find that really intriguing and interesting in causal inference, that I can not only look in people's backyard, I can even look in the kitchen.
How important is it to reconstruct clinicians' intent when trying to understand different patient populations? And how can you be confident that you have done so correctly?
So the problem with no unmeasured confounding is that you cannot test it. There is no way, because if you miss a confounder, you don't have it, so you cannot see whether you miss it. So you really have to rely on the subject matter expert that he or she or a team or the team has come up with enough confounders and that they're all there. So I often don't restrict these sessions to just one session in which we talk about confounders. We talk about confounders, we create a list, we get back to it, we update the list. And over the course of time, this comes back. So before it gets published, before we send it in, we go over the confounders again. Are we really thinking that we have the most important ones? And I think that's why causal inference can most of the time really not replace randomized clinical trials, because we don't know that we have all the confounders. We can never be sure. And even if we had all the confounders, we are not even sure that we put them in the model in the correct way. For those of you who know regression analysis, if I have two variables, there's so plenty of ways in which to include them, even in a regression model. So we often don't know for sure. And I think that's why we cannot replace randomized clinical trials with causal inference methods. It's also a big reason of why we often try to analyze data more than one way, because maybe our models are wrong. Maybe the overall assumptions could still be right, but maybe our models are wrong, because most causal inference methods rely on some kind of model assumptions.
Have you ever refused to provide your services for any reason, or for a study that you felt was too ethically or conceptually flawed to improve by consultation?
Yes, and I will not say who.
Thank you. We have a more general question here. Can you share a little more about the latest development or challenges for the technical or application aspects of causal inference?
Oh, there are many. I think that's why I call my book Causal Inference, a Statistics Playground, because causal inference has a lot of applied aspects to it. It's watching what people are doing, figuring out why they're doing what they're doing, and very interesting and intriguing real-life, real-world questions. But then there is also the statistical aspect of it. We can show things like consistency and asymptotic normality, and the bootstrap works. So what does all that mean? That means consistency means if you have a lot of data, you can get close to the truth with as high a probability as you want it to be. So you can say how close you want to be. You can say with how high a probability you want to be there. Well, if you have enough data, maybe you have to have more data than there are humans in the universe, but whatever. If you have enough data, you get that close. So that is kind of a first guarantee, or not guarantee, but a first wish that you would have for an estimator, that as you get more data, you get closer and closer to the truth. And then there is also this thing called asymptotic normality. For many of the estimators that are there in causal inference, we can show asymptotic normality. What does that mean? That means that if we get more and more data, the estimator is approximately normally distributed. What does that mean? Nice bell curve. And we know the distribution. That gives us a guarantee that our confidence intervals, so these nets with which we try to catch the parameter, that these confidence intervals decrease at a rate that is 1 over the square root of the number of observations. That's pretty fast. And then the bootstrap works. Well, the bootstrap is kind of a weird method where we resample from the data that we already have and use that to create confidence intervals. So it's kind of a weird method, but it can be used to create these, to calculate these confidence intervals, because we know that we can create confidence intervals that go like 1 over square root of the number of observations, so that are shrinking. But then the next step is how to calculate those. And causal inference is especially difficult there because we have maybe a parameter of interest that we want to estimate. Maybe it's the treatment effect. But then we have also these methods, like how to calculate those weights. Well, for that we have to estimate the probability of Casavi for given patients, and we have to estimate the probability of colistin for different patients. These we call nuisance parameter models. We fit models, statistical models for that. And it turns out to be fairly difficult to include the estimation of these nuisance parameters into the creation of the confidence intervals. So the bootstrap helps there because you just resample the whole thing and do your analysis again and again, and then take quantiles, if you know what that means.
Thank you again, Judith, for your interesting presentation and perspectives. And I would also like to thank our audience for your wonderful questions. I hope you will be able to join us for other Radcliffe virtual programs. You can find out about the future programs and watch videos of past events at radcliffe.harvard.edu. Thank you again for joining us, and have a great rest of the day.